Hi, I am Sagar. In this video, we will discuss solution for few previous year gate questions on combinational circuits. This question asked in GATE ECE 2012 1 mark question MCQ. The output Y of a 2-bit comparator is a logic 1 whenever the 2-bit input A is greater than a 2-bit input B. The number of combination for which the output is logic 1 is. So the output will be 1. Output will be 1 when if A greater than B. Only A greater than B. So for example, if we consider if B is equal to 0 0, the 2-bit comparator. If B is equal to 0 0, then there will be 3 combination for which the output will be 1. That means when A is equal to 0 1, 1 0 or 1 1. Similarly, if B is equal to 0 1, here also two condition. When A is equal to 1 0 or 1 1. For example, if B is equal to 1 0, then we have one condition when A is equal to 1 1. So the question asked the number of combinations for which the output is logic 1. Clear? So we have completely how many here? Here 3, here 2, here 1. So total 6 combinations are there when A greater than B, the output equal to 1. So option B is the correct. This question asked in GATE ECE 2014, set 3, 2 mark question. If X and Y are inputs, the difference D is equal to X minus Y and the borrow B are the outputs. Which one of the following diagrams implements of subtractor? So now if we see the truth table of subtractor, the difference is 0 when both inputs are same. The difference is 1 when both inputs are different. So we can write D is X XOR Y. So X bar Y plus Y bar X. This is the equation for difference. If you see the borrow, only for this combination, the borrow is 1, nothing but X bar into Y. So that borrow B is X complement into Y. So we check individually for each option. So we know that general equation for mux Y is equal, if S is the selection line, S bar into I naught plus S into I1. Now if you see the option A, the X is the selection line, so that I naught input is Y, I1 input is the Y complement. Clear? So now the difference D, we can write X bar, X is the selection line into I naught inputs, nothing but Y plus X into Y prime. So nothing but this is the X XOR Y difference. Similarly, borrow B is equal to, so same X is the selection line for this mux also. So X bar into Y plus X into 0. Here 0, this is the Y. X into 0. So B is equal to X bar Y. So option A is the correct. No need to check B, C, D options. This question asked in GATE ECE 2014, set 3, 2 mark question. In the circuit shown, W and Y are MSBs of the control inputs. The output F is given by. So they give simple 2 4:1 mux. So now the output of first mux is the Q. So W and X are the selection, right? Sir, 4:1 mux, the output Q we can write. So where W or X are the selection line, W bar X bar I naught plus W bar X into I1 plus W into X bar I2 Wx into I3. So now if you see, I naught is 0, I1 is 1, I2 also 1, I3 is 0. So simply we can write, so W bar X bar is the 0. So W bar X I1 is the 1, W X bar I2 is the 1, Wx I3 is the 0. So this Q we can write as a W bar X plus W X bar, simply W XOR X. For second 4:1 mux, the output Y can be written as where Y, Z are selection line. So Y prime, Z prime, I naught, Y prime Z into I1 plus Y into Z prime I2 plus YZ I3. So here I naught is Q, I1 also Q, I2 is 0, I3 is 0. So simply we can write Y complement Z complement into Q plus Y complement Z into Q. So Y Z complement 0, YZ 0. So we can write Y complement Z complement Q plus Y complement Z Q. So we can common this Y complement Q. So Z plus Z complement. Anyway, Z plus Z complement equal to 1. So we can write F is equal Y complement Q. But here Q is nothing but W complement X plus W X complement. So that final answer F can be written as Y complement into W complement X plus W into X complement. So here W complement Y complement X W Y complement X complement. So the option C is the correct. This is a very simple question, that to 2-mark question. This question asked in GATE ECE 1997, 1-mark question. A 2-bit binary multiplier can be implemented using. So now I consider two 2-bit binary number. One is x1 and x0, another number is y1, y0. If I perform multiplication, so x0, y0 and x1, y0, and then next y1, x0, so y1, x0 and y1, x1. You can write, so y1, x1. So now we can write this is the output. So we can write this is the output C0. Now this is the C1, this is the C2. But if we see here, so we need to perform addition. So here we required one half adder. So we'll get some carry. Okay, we'll get some carry. Here also we need one more half adder to get this C2. If we get any carry, then that we have one more digit here, C3. This is the final output. This is the simple, okay, 2-bit binary multiplier. So to perform this 2-bit binary multiplier, so we need 1, 2, 3, 4, 4 AND gates. We required 4 AND gates, and also we required 2 half adder. This one half adder and this is a one more half adder. We required 2 half adders to get output. In to implement this 2-bit binary multiplier, we required 4 AND gates, the two input AND gates and 2 half adders. 2 half adders nothing but here this half adder nothing but XOR gate only. XOR gate only. XOR gate and OR gate anyway. So that the appropriate answer, that option B is the correct, 2 input XOR and 2 input AND gates only. Now if we see the implementation of 2-bit binary multiplier, so here we required 4 AND gates and 2 off adders. The 2 off adders contains XOR gate only. So option B is the correct option.